And thank you everyone for joining me this afternoon for this talk about debugging and optimization of PyTorch models. Specifically, we'll be focusing on a tool called PyTorch Profiler, which is built into PyTorch, and that can help us identify bugs and optimization targets in our deep learning workflows. This presentation is available currently on GitHub. After the presentation, I'll be adding the example code so that you can run some of these examples yourselves. All right. For this presentation, we're going to start by talking about why you should profile and optimize PyTorch code. And then we'll think about when we should start profiling and when we can think about optimization. And then we'll get to the tool PyTorch Profiler. We'll go over some basic profiling and then kind of dive deeper into generating and analyzing full traces. And we'll talk about memory profiling that's available through PyTorch Profiler. Lastly, we'll look at a tool called holistic trace analysis, which PyTorch recommends for analyzing the PyTorch Profiler traces. It can give you just some deeper analysis and some better comparisons, and provide you with data frames that you can do some of your own analysis on for aggregating data across runs. And then we'll finish off with a Q&A. We'll aim for about 45 minutes, so we have 15 minutes for questions. But yeah, let's jump into it. So why should you profile and optimize your PyTorch code? Profiling allows you to understand how your model is running. You can see how data is flowing between the main memory and the GPU. You can identify performance bottlenecks and find bugs, things like bad data flows, CUDA out-of-memory errors, regular out-of-memory errors, all good things. It's a good idea to see how your algorithm is running on the system so that you can make sure that everything is operating as you expect in your algorithm. And we do this so that we can find targets for optimization and increase our efficiency. And that allows us to have greater research throughput, which is good for everybody. But it also lets us make full use of our allocated resources. When we ask for resources on the clusters, we want to make sure that we're making full use of those resources because we're being charged for them with respect to our priority. So we want to make sure we're being as efficient as possible. And that's also good for everybody. Okay, so when should you think about profiling and when should you think about optimization? And I'd argue that there's many reasons to profile early. And that's because profiling can help with debugging. So before your algorithm is even fully functional, profiling can help you find those problems like memory issues and bad gradient and data flows and that sort of thing. It can also help you estimate required resources. So maybe you have a prototype of your algorithm and you've been running it on smaller data sets. Profiling and those smaller data sets can help you estimate how large you can make your batch size for making full use of the GPU, how long your algorithm will run on the full data set and that sort of thing, which is helpful because we want to avoid out-of-memory errors and timeouts and that sort of thing. And it can also help you identify bottlenecks that are occurring outside of your training loop. So kind of outside the scope of whatever algorithm you're working on and kind of eliminate those early on. And now once you have a working training loop, you can start to think about optimization. Some of the optimizations in PyTorch are very simple and can be applied early on without really affecting your ability to develop it later. And this will help with moving beyond that prototype phase into full run efficiency and gets you ready for hyperparameter tuning. When we're talking about doing full runs across large data sets many times to find optimal hyperparameters, any sort of gain we can squeeze out of every iteration really helps us as far as total time and resources that we're using for things like hyperparameter tuning. We also want to think about, are we going to be modifying our model operations in a way that we'd have to redo optimization. And if you're in that position, you probably don't want to think about optimization yet, and hold off until you've kind of finalized the main workings of your algorithm. So let's talk about the tool, PyTorch Profiler. It's built into PyTorch. So if you've installed Torch in your virtual environments, you already have access to PyTorch Profiler. You can profile your runtimes, memory, and generate detailed traces of PyTorch code. And this allows you to see a layer-by-layer breakdown of your model performance. Provides both CPU and GPU profiling, both computation and memory. And it does require some small code modification. In general, you just need to wrap code with a context manager. And right now it works for NVIDIA and AMD GPUs. I was running this on Narval, so using the A100s there. So all of the examples you'll see here were NVIDIA GPUs and CUDA. For basic usage, you import your required packages. I'm instantiating here a random ResNet 50 model from PyTorch, from Torch Vision, sorry, and giving it some random inputs. And then I use context managers to run my profiler. And we'll kind of get into the details of this in a bit. So we'll run that. Now, I just ran random inputs here on my laptop using the CPU through ResNet 50. The main kind of like simplest output we can get are these key averages tables, which takes a argument sort by. So here I'm sorting by the total CPU time, and I can see, you know, the various layers that have been running in ResNet. Self CPU percentage and self CPU. The self there refers to that for, you know, this convolutional layer, say anything with self, it's just what's running in that layer. If that layer's calling child processes, those aren't included in these self measures. So yeah, we can see a breakdown, the number of calls that went through, total percentage of time. You can kind of see which layers are really costing you the most time, and, you know, the total time that it took. We can also, if I go back here, a parameter that we get, or an argument that we gave the profile, was record shapes equals true. And that allows you to record the shapes of your inputs as they flow through the layers. So if we generate our table showing the input shapes, it's very wide, so unfortunately it doesn't format very well in this notebook, but you can see the input shapes of the different layers, which can be handy because if you know what your shape should be, you can kind of debug those shaping problems using that. Okay, so that was a very simple example just running on my laptop here, but let's think bigger and run on a more complicated example. So here we're running ResNet validation on the ImageNet dataset. We'll be using pre-trained weights provided by Torch Vision. We're using a batch size of 1024 on a A100 on Narval, but we're using the 4G 20 gigabyte MIG instance. In general, we're using greater than 16 gigabytes of CUDA memory during this. I've included the code here. The details don't really matter. I'm assuming you're familiar with PyTorch and you know, can recognize you know, training or validation loops, moving data through models and loading data with data loaders and transforming data. I'm assuming you know all of that. And the details that matter here are kind of what we're using for the profiler. And we'll go through those in detail as we go along. So the first kind of detail we need to know about is scheduling in the profiler. And we need this because for long-running jobs, if we capture everything, the trace files that we might be generating will be extremely large. So we want to, capture a subset of our training iterations or validation iterations, rather than capturing the whole trace, to limit those file sizes and prevent them from becoming almost unusable. And the way we do that is with a schedule. We provide this to our profiler in an argument. And what this specific example will do is the profiler will skip the first 10 steps, then it will wait 5 steps, and then it'll perform a warm-up of 5 steps. And this allows the kind of us to not capture some of the overhead from the profiler as it comes online, and gets ready for actual capture. After the warm-up, it'll capture 5 iterations. And then here we've set repeat to 1. So it'll just do 5 iterations once, and then it will be done. But if we set this to like 2 or 3, after our active capture, we'll go back to our wait and wait 5 steps and then repeat our capture. And that'll go for as many times as you set repeat. If you set repeat to 0, it will run through, it will capture the entire, it will run through the entire it will run through all of the iterations that you step through. So you'll follow the schedule through the entire schedule, or through the entire training or validation. There's also the record function, and we use that in a context manager as a sort of labeler for processes. So here I'm profiling this entire code block, but I'm using a context manager over passing data through the model and labeling it model inference. And that way I can kind of capture a block in my traces that encapsulates everything involved in this process. You could, if you have a training and then validation loop, you could, use separate record function for those. So you could have a capture all of your training and get like total times and percentages for those, and then have a record function and then label it, validation, and capture statistics about that whole process. It's just kind of a convenient way to label our traces. So when we're not looking at a single process or function call, but we want to see, how long does this whole code block take? We can give it a label and see that. So if I run this is from a CUDA run, ImageNet validation on Narval. We're outputting the table here. I captured both the CPU and GPU using the profiler. I've eliminated the CPU output here because the table is too wide, and we're kind of more interested in the CUDA usage here. Same deal here. Self refers to just the computation that's occurring in that module, not calls to child processes or anything like that. We can see memory usage, which we set by setting memory profile to true in our profiler. And we get our total times on the CPU and in the CUDA kernels. So this is, sort of interesting information. Maybe it's a bit crude. We can see the labels for model inference here. I'm not sure why it's showing up twice. It's only in the context manager once. Maybe there's a bug here that we need to figure out. But yeah, the tables are very basic and don't give us all that detailed information. And if we printed out the whole table, all of the rows, we'll be seeing every layer and every kernel being called, and it's kind of unwieldy. If we want to get deeper into what's going on, we should start generating and analyzing traces. So the profiler has the ability to export a Chrome trace that you can view in the Chrome browser by navigating to Chrome tracing and then loading your trace. So in the code, we just save those traces and we'll take a look at some of those. So by way of a case study, let's look at the GPU idle time from our first run. So first run here, I'm looking at a serial job uh, doing validation on ImageNet. Our tool, we load the trace, and okay, this is kind of overwhelming. We see all sorts of things here. I know the font size might be a little small, but if we click on one of these blocks, we can see more detailed about what's in there. We have CPU at the top, GPU on the bottom. There's this toolbar here that we can use, a selector or a pan, so we can pan our trace back and forth, or there's a zoom, so we can zoom in and out on our full trace. We zoom in here and then select this, kernel that we can barely read. We can get the full name and see what's going on there. So let's just zoom out here. The final tool, zoom out. Final tool we have is this measurement tool, so you can set bounds. And here I've done that for the full run, and you can see it took 16.7 seconds for these 5 iterations that are recorded. But the main thing we notice here is that our GPU is not busy at all. It's idle for most of the runtime, and we're spending most of our time in the data loader. And that's because we ran this as a serial job. So our solution is to just ask for more cores in our job script and to provide more workers to our data loader so that we're not starving our GPU. And indeed, with these MIG instances, it's recommended that the maximum number of cores on Narval for these is 6. So I just upped it to 6. And here, I have the full runtime now is 4.9 seconds, which, is quite a bit of a difference. It's more than 3-fold difference. And if I say, by way of demonstration here, I can measure this profile step was 845 milliseconds. If I measure it here, it's 3.434 seconds. So we're getting a significant speed up per iteration, and that's demonstrated across many iterations. You don't want to generalize too much over a small sample size, but I only collected here just for I only collected 5 iterations here for the purpose of demonstration. If we go back here, though, we notice that we're still coming across this data loading problem every once in a while, and we're getting some GPU idle time. And this is kind of our next case study. What's going on here? We're still seeing this pause in training. We added cores. What's the problem? And the problem might be that we simply haven't added enough cores, but we might also be running into limitations of the file system here. We really need to kind of collect more data, maybe collect more traces across more iterations, see kind of how often this is occurring. But over these 5 steps, we saw a 3 times speed up even with this waiting. So this whole this starvation period here, 785 milliseconds, whereas a starvation period here is 2.6 seconds. So we're still starving the GPU for some reason, whether that's just the cores can't keep up with the data loading or we're running into file system issues. But we're still, faster overall, and that's the effect of those cores on the data loading. Okay, so for our last case study here, we'll look at the effect of optimization. And kind of the simplest optimization you can do in PyTorch is to just compile your model. So after you've instantiated your model, you just call torch.compile on the model, and that will optimize the the model. It will turn off the eager execution, so we don't have to worry about the shapes of the data or types going in. It'll kind of locks those things down, so it gets rid of a lot of the overhead involved in running a model, and that provides speed up. You can also compile user-defined functions, and if you look in the PyTorch documentation, they also talk about optimizing compiling the optimizer. And the way to do that is to wrap the step function in a user-defined function, and then you use a decorator to compile it. And this is how you would also compile a user-defined function. So if you have a function that's a bunch of torch code, it's not necessarily a nn.module class or anything like that. You can provide this decorator, and the torch will compile that code for you. Yeah, so if we now look at our third trace here, we have a trace where, again, we're using 6 cores, and but now we're compiling the model. You can see our total time is 4.4 seconds for the 5 iterations. We're kind of missing a little bit here, so we'll call it 4.5. And then if I go back to just our threaded job, it's 4.9. So we're saving half a second over 5 iterations here. Again, we don't want to generalize too quickly, but there is some speed up there. But really, we want to kind of narrow it down. We can take a look at a step here, kind of a normal step without this starvation. And you see here it's 617 milliseconds, whereas here we're at 845. So we're 20%-ish increase. So, you know, that's for how simple this optimization is, we're maybe getting a lot. And the other thing to notice is that this starvation is coming up more often. And maybe, again, we don't want to generalize. This cause for maybe further investigation. But seeing as our model is running faster, maybe the data loader is having even more trouble keeping up with the model and not starving it. And, you know, we want to investigate why. Do we need more cores, or are we running into limitations of the file system? If we're using Project or Scratch, can we use the node local storage? Those sorts of things. All right, so with memory profiling, you can use profile memory on its own, and then it will be output in those tables when you print them. But if you want to get a more detailed like plot or trace of the memory, you'll also need to include this with stack. So set those both to true when you instantiate your profiler. And then one way to export them is you use this export memory timeline function. And if you give it an HTML extension, it will generate an HTML file that contains a PNG plot of the memory usage. I'm not sure why it's done that way, but that's the way it's done. And you can also use a .json extension, and then it will output a JSON file, which you can then parse yourself and plot in any way you want. So you're not kind of stuck with the plot that they give you. But for this, we'll just use those HTML files. And also, because we're talking about memory profiling, memory usage during inference isn't all that exciting. So we're actually going to pivot to training ImageNet on training ResNet 50, on ImageNet. Again, we'll use a batch size of 1024. We use stochastic gradient descent and generate memory plots then we can generate a memory plot based on the trace. So here I've captured 10 iterations, and there's something wrong with our model. And for those of you that are familiar with kind of these flows and how these training iterations should work, does anyone have any idea what might be wrong? I have the more blown up version here. We have, a breakdown of what's being used. We have our parameters that remain constant. And then we have our optimizer state that remains constant. And then as our iteration begins, we have the activations begin to grow. And then this would be where our back propagation would start and our activations start leaving. So can anyone see the problem here? It might be more obvious if we look at a non-bugged model. So the problem is that in our bugged model, we seem to be carrying the gradients over as we go. And this is causing an increase in the memory usage. So if we're operating with a really tight window with our CUDA memory usage, this might be enough to push us into a CUDA out of memory error. But it might also cause other problems with how we're using our gradients, depending on how we're keeping them. So the problem here is that we're keeping those gradients over iterations and never clearing our optimizer. You can see this would be our normal flow. We have our activations beginning, back propagation starts, and our gradients start accumulating. Our activations get flushed from memory, and then we clear them. So that's just an example of a very simple example of memory debugging. We got our normal iterations, and all we had to do was remember to zero our gradients. But if this is a mistake we make, then we can catch it with these memory traces. Okay, so let's talk about our final tool. This is holistic trace analysis. It's recommended by PyTorch for analyzing the traces from Profiler. It's a performance and visualization library. It uses traces from PyTorch Profiler to provide a more detailed analysis. Specifically, it's better at comparison between traces, and it's also highly optimized for analyzing distributed workflows. So if we have multiple GPU instances and we're running traces on all of them using the profiler, then HTA can do comparisons between those traces, and you can find out where your bottlenecks are occurring and that sort of thing in your like broader distributed workflow where we might come into communication problems. But you can use it to analyze the traces we've been producing so far, and I'll show you how to do that. It has many features, but I'll just focus on these three: the temporal breakdown, the idle time breakdown, and the trace diff that compares traces. All right, so we install our HTA library, and then we import our trace analysis object. We tell it where we're keeping the traces, and it will read in to that directory, grab the traces here. You can see the traces include you can see I ran this on Narval, and it gives us just stats about how long it took to import and all that stuff. Some important things to know is to be able to use it, we need to use a trace handler. And PyTorch has this built-in TensorBoard trace handler that was intended to integrate these traces into TensorBoard, but they no longer support that integration, but this TensorBoard trace handler is kind of left over. So I suspect maybe it might change its name eventually. And you give that trace handler, a path where you want to save those traces, and you can tell it to compress the output, which is probably a good idea, especially if you're running very large traces. And then you just provide that trace handler to your profiler when you start it in the context manager. And if you're not running a distributed job, HTA expects there to be a rank information in the JSON file. So if you're kind of just running it on a single trace or some kind of unrelated traces, you'll have to add this entry into the JSON file, just added at the top. And if you have multiple files from different runs, you'll need to use a different rank for each file that's in the directory that you're loading them from. Okay, so let's talk about the first feature, temporal breakdown. We use temporal breakdown it gives us a data frame, and it also plots the temporal breakdown. And here, rank 0 is that serial run that I showed the trace from earlier. Rank 0 is 0. Rank 1 is our 6 workers. Rank 2 is our 6 workers, and it's compiled. You can see that the decrease in the overall percentage of idle time. You might look at this and think, oh, the compilation is causing us to spend more time in idle, which is true as a percentage. But really, if we look at this data frame, we kind of get a more complete picture. And we can see that actually the idle time between the two is somewhat comparable. They're fairly close, but the overall compute time for the compiled run is way less, and that's causing the skew in this overall percentage. So I think from having used this tool that the data frames are actually kind of more important than these plots. They give us more information, and you can do your own analysis looking at these plots. But if you ran this analysis before looking at the trace, you would see, okay, I have a problem here. I'm at almost 75% of my time is idle time. Something's going on. I'm starving my GPU, or it's waiting for something. So you can use this tool without having to look at the trace, that sort of thing. It's just kind of preference, what you like to look at. Yeah. So the next feature we'll look at is idle time breakdown. There's 3 categories that are generated by this feature. There's host wait, which is the idle duration of the GPU that can be attributed to waiting for the CPU, whether that's in queuing kernels or memory copying and that sort of thing. And if you're running into a case where you're seeing lots of host wait time, you want to examine what CPU's processes are causing the slowdown and increase the batch size. The kernel wait time constitutes the short overhead that's used to launch consecutive kernels on the GPU. If I just go back to this trace and zoom in here on our GPU, collapse that, you can see many kernel calls in sequence. And for each one of those, there's a small amount of overhead that you pay for launching it. And you can use something called coup de graph optimizations, which is another fairly simple optimization that I don't have time to get into here, but you can use a coup de graph optimization. And what that does is it groups the kernels together and provides one launched instance. So you're paying for the overhead once instead of at every kernel call having a small amount of that launch wait time. You're just grouping it together, one launch, and that can save you time if that's where you're finding problems. And the third category is other wait time, which is just things that wait time that holistic trace analysis couldn't identify due to lack of information. So Could be, things beyond waiting for the CPU or these kernel wait times. I suspect as HTA gets more and more developed, they'll probably start adding categories as they come across, those things. Okay, so if I look at my idle time for those three runs, again, rank 0 is our serial job. No surprise here. 100% of our wait, our idle time was in post waiting. So if we're looking at a target of optimization here, maybe doing coup de graph optimization isn't necessary at this point. We're clearly being dominated by the host wait time. So we need to address that issue first. And actually, for our threaded jobs, compiled and otherwise, it's the same thing. 100% of our wait time is due to starvation of the GPU. If we look at the data frame, we can see that while the percentages are the same, the absolute numbers are quite a bit different. We saw these numbers before, but now we can actually see the kernel wait time for each of these. And actually, because of the optimization, we are already saving a little bit on because of the compilation, sorry, we're saving a bit on the kernel wait time. But maybe if we're thinking about optimizing our workflow, we need to tackle these problems definitely first before we move on to worrying about kernel wait time. Okay, so the last feature we want to talk about is trace diff. And with trace diff, you give it a control folder and a test folder. So again, this is kind of built for that distributed workflow. So it's expecting multiple traces from a single multi-GPU run, but you can, kind of split them up however you want when you're comparing non-distributed runs. You just have to define a control folder and a test folder, put the traces you want to compare in those folders, and then you can compare them. Here, we're going to test our parallel, threaded run, and then against the compiled run. And this, we're comparing the traces by the different number of call counts. And then we can use this visualize counts diff function to kind of visualize that difference. And kind of no surprise here, these two traces are wildly different because we've compiled one of them. So anything here with inductor, those are the compilation, has to do with the compilation. So we're seeing a big difference in calls. For most of these, the control, the non-compiled run isn't running anything. So maybe for comparing these traces, this isn't overly informative. But if we're comparing traces between algorithms with small differences, or say we have, we're comparing two runs on different nodes, we can see how, those sorts of things differ. Or between GPUs, you could trace on a full A100 and then on a MIG and kind of see how the traces are differing. Counts isn't the only thing you can visualize with this. There are other options. And I'd invite you to look at the documentation to see everything that's available. Speaking of everything that's available, we have a host of other features that we can look at that we just didn't have time to get into today. You can do a kernel breakdown. So what kernel calls are being made. You can look at the kernel duration distribution. This could be useful for comparing GPUs, for instance. And then there's the communication computation overlap that would be more important for distributed job. And then CUDA kernel launch statistics that can help you look at maybe how you want to do like CUDA graph optimization, how useful that would be, that sort of thing. Something called augmented counters, which just kind of augments the trace. Frequent CUDA kernel patterns, Kupti counter analysis, and then this lightweight critical path analysis, which I kind of these is maybe one of the more interesting ones. If we did that lightweight path analysis here, we'd see the critical path moving. It would generate a critical path moving through this trace. So you'd have blocks highlighted here in sequence. And if you look along that critical path, that would be where you could make the most up in optimization. Speaking of these traces, there are a few, there are some features that I didn't go over. So up here, you can save a trace. I'm not sure with this, you wouldn't necessarily need to do that. It's fairly static, but when you're loading a trace, you just click load and then load your JSON file. But here though, we have flow events. And if I click all, now we can see where data is moving through, between GPU and CPU, flows across, and that sort of thing. So if you have some workflow that's maybe more specialized, I come from a reinforcement learning background where if you're not careful with how you're moving information between, say, your actor and critic networks and that sort of thing, you might have odd flows. So you'd be able to visualize those sorts of things using the trace. So that's just something I wanted to mention here too. If you find it's just in the way, you can just disable it. See processes. I can, not look at CPU. Those are handy features there. Okay, so yeah, if you want to know anything more about holistic trace analysis, I definitely recommend reading over their documentation. There is a lot there. Each of these features has, sub features to look at. So definitely not enough time here. With that, actually, we're pretty much hang on at Q2. So we can go for Q&A here. As I said, you can look at the GitHub link, which I'll paste again for a copy of the presentation. The example code and job scripts aren't there yet, but I'll be doing that immediately after the presentation. But yeah, we can probably stop the recording and open it up to questions.